Hello students, in this video we'll discuss simple linear regression. In this setup we want to consider a collection of data points. x1, y1, x2, y2, x3, y3, xn, yn. We consider n data points. In this situation, we're going to think about the x variable as an independent variable, trying to describe a dependent variable y. We think of x as an explanatory variable, trying to explain a response variable y. Now we can draw a scatter plot of these points. So let's draw a scatter plot. There's y and there's x, and this is going to be a scatter plot. And we might get something like this. And from this scatter plot, we might deduce that there might be some linear relationship between x and y. And remember what a linear relationship is. A linear relationship is just saying something of the fact that y is equal to a plus bx. That would be the equation of a line, or mx plus b. We might think that there's a linear relationship, and so we postulate that there's a true linear relationship. So we say that there's a true, we'll put that in parentheses, linear relationship that experiences some error, that experiences a normally distributed error. That is a fancy way of saying that if I think about my y as my response to an explanatory variable, my y is a random variable. That's a random variable. And the random variable seeks to be explained by a linear relationship, which I'm going to do beta 0 plus beta 1 to stay consistent with most notation in textbooks, of a random variable x plus an error. And this error over here is a standard normal, with mean 0 and standard deviation equal to sigma. And we want this to be a constant standard deviation among all these samples. And so what we can say then is we can use this to denote the fact that in some true sense that yi is equal to beta 0 plus beta 1 xi plus epsilon I. And we're going to think of these epsilon I random variables. So the epsilon I are identically distributed and independent, and normal 0 sigma squared. Now this is our true relationship with some error in our sort of modeling. What we seek to do is we want to try to estimate. So the goal of linear regression is to estimate these parameters beta 0 and beta 1. So the goal of linear regression, so our goal is to estimate beta 0 and beta 1, which are not known to us. These are unknown parameters in our problem. So these are unknown to us. I need to estimate them. And the approach we'll do is we're going to approach this by using the sum of squares difference. So we're going to look at the error sum of squares. And what is the error sum of squares? We're going to try to find, our goal is to try to find estimate beta 0 by looking at yi, which is something we estimate b0, an estimate of beta 0, plus b1 xi. And we're going to call this yi hat because it's an estimate. So this is our estimate of what? Our yi hat estimates the parameter yi. And so what we can do then is we're going to look at the error sum of squares in this problem. And the error sum of squares is going to be the sum over all of our observations, j goes from 1 to n, of the actual observation, yj, that's our actual, minus our estimate of it from this problem, yj hat quantity squared. That's the error sum of squares. And my goal in this problem is to find b0 and b1, so we find these estimates, we find b0 and b1 by minimizing this error sum of squares. In future videos, we will use calculus to figure out exactly how we minimize this error sum of squares. So linear regression takes a data collection. It postulates that there's a true line that goes through the data points up to what? Up to a normally distributed fluctuation. And then what it does, it makes a estimate of those parameters beta 0 and beta 1. And these estimates, b0 and b1 of beta 0 and beta 1, are chosen in such a way such that the actual response, yj or yi, the yi response, minus the predicted response using this regression tool, quantity squared and added up is as small as possible. So we seek to minimize the sum of squares of differences of the actual minus the predicted. And we'll see in future videos how we actually compute these beta 0, this b0 and b1 as the estimates of beta 0 and beta 1. Thank you very much.